Thank you, everyone. So as Victoria mentioned, my name is Ali Kanso. I'm a principal engineer at Microsoft. Today, I'm going to talk to you about different shades of using KubeRay. At the beginning, there were 6 shades, and then I had to drop them down to 3 just to fit within the time of this presentation. So the 3 phases would be, 1, using KubeRay as one-stop solution. Then we're going to go into using KubeRay as a building block of a bigger solution. And finally, we're going to go into developing applications on top of KubeRay and how we can use the Python SDK to do that. OK, so if we take a step back and just look at Ray from a high-level point of view, you would consider Ray as just a platform that ingests data. It could be live data or simulated data. And then you produce a model, and then you can infer information and insights from this model. So the point I want to focus on here in the first part of the talk is the duality between data and simulators. So now, if we take that view now, expand it further, you would realize that there are different actors there. So you have the Ray core with the Ray code running in there. You would have your app layer, which is your code. That's your machine learning code running there. You would have some data that's not yet ready for training, so you might need to pre-process that data. And finally, you would have some simulators, which is probably someone else's code from a lot of the experience we've been seeing there. So if we take that exploded view and we just look into it from a horizontal point of view, you would have at the bottom layer the physical cluster or virtual cluster, depending on how you're setting up your compute cluster. On top of that, you're going to have your Kubernetes cluster. And then this is where your Ray clusters are hosted. So a Ray cluster from that perspective is just a bunch of containers that are running inside of your Kubernetes cluster. On top of that, you have the Ray runtime that's running inside the Ray cluster on top of your Kubernetes cluster. And finally, you have your ML code. So that would be the high-level vertical view of the system that we are working with. Now, if we take that view and we put it horizontally, you would have Kubernetes at the bottom. You would have your Ray cluster and your application code. And this is KubeRay territory, the one that's highlighted there. So this is what KubeRay is intended and conceived to manage, your Ray cluster and your application. You would need some simulator pods, because simulators are executable. They need to run somewhere. So why not run them as pods in the same cluster? And then you're going to have some data processing pods, because if you're using some data processing engine, then that engine needs to run somewhere in order to process your data. Now, since I'm going to be talking about KubeRay, I might as well give a high-level introduction. And there's a really good talk at 4 p.m. if you want to use it.
Use that microphone, please.
Do I need to remove the?
No, turn it off, or you can pin it back on your shirt.
I pinned it back.
It's got to be higher up.
OK.
There, right up there. I apologize, sir. Thank you, everybody.
This was demo number 1. So moving on, KubeRay, in a nutshell, so it's just an orchestrator for Ray clusters. So KubeRay is a Kubernetes operator. How you interact with KubeRay as a user, you would define your cluster definition. This cluster definition, it's going to be a custom resource. You specify in the cluster definition what type of cluster you want. And KubeRay has mainly 3 interfaces. It has one interface always listening to the create, update, delete of Ray cluster definitions, and it reacts to that. It has another interface where it uses that interface to create pods and services and so on using the Kubernetes API server. And the third interface, it watches cluster events. So if your pod fails, for example, one of the KubeRay worker or Ray worker fails, it's going to restart that pod for you. So this is in a nutshell KubeRay and how it sits in that grand scheme of things there. Now, we talked about KubeRay, but what is a Ray cluster in the context of Kubernetes? So we mentioned that you're going to, as a user, define your cluster definition. You're going to, somehow, it's going to reach KubeRay operator. What KubeRay is going to do is going to create a Ray cluster. The Ray cluster is just a bunch of pods. And there are a bunch of pods configured in a special way. So you would have the Ray head pod. That head pod is abstracted by a head service, which is a Kubernetes service mainly used to maintain a DNS name for that head pod so that it's easily identifiable by the workers. And then you'd have one or multiple worker groups, each worker group consisting of one or multiple pods, and they all are configured to identify the head pod, and they would register with the head pod, and they would form a cluster once they are instantiated. And that's in a nutshell how array cluster would look like. And today we're going to create a bunch of those clusters during our demos. Now I want to circle back to the simulators a bit. So imagine you have a reinforcement learning environment, and now you are feeding it data. If that data is coming from a simulator, then there are a few options there. It's either a third-party simulator, like Microsoft AirSim is one simulator example. That's a third party. You can use Simulink with MATLAB and so on. So that's not your code. That wouldn't be your code. You would have an in-house standalone simulator, for example, if that's another team in your organization that have created that simulator. So it can run as an independent executable, not part of your machine learning code. And finally, it could be integrated within your machine learning code as an in-house integrated simulator. So let's assume the first two examples, if it's a third-party simulator or if it's a standalone simulator. Now, if you have an agent that's running and you're doing some reinforcement learning training there, you might have for each state multiple actions. So for simplicity, let's assume your actions are move left, right, or go straight forward. At each stop, you don't need to use a single simulator to train your policy. What you can do there is simply have multiple simulators running at the same time for each potential action at a given state, and that would speed up your training process by a significant amount of time. So what I'm trying to say here is that the cardinality of simulators versus the agents you have doesn't have to be one-to-one. Another example there is assuming you're training multiple policies at the same time. You might be using multiple simulators at the same time and just doing your training in parallel. I mean, after all, it's a distributed system. Ray is doing the parallelization for you, so why not take advantage of that? So the point I'm trying to drive forward here is that sims can be deployed independently of your Ray application, and they can be auto-scaled during this training process. So they might have their own life cycle where they grow and shrink and so on. And you need a way to manage those. And the question is, how would you be managing those simulators? How would you deploy them, and how would you scale them? So this is where I want to take an unconventional view here. Because everyone, when you think of KubeRay, you would think of a Ray cluster manager, which is managing a head node and a bunch of Ray worker nodes. But what if we change that view a little bit? In this particular example, what I'm showing here in this manifest, on the top-hand side, you would have the Ray head definition. Then you have multiple worker groups. One worker group, we call it small group, and it has two replicas. But at the bottom level here, you see we have a simulator group. And if you look at the image there, that image is not a Ray image. That doesn't include Ray code whatsoever. Yet you can still define it as part of your cluster. And when you create your cluster, you're going to have now 3 replicas of that simulator. When you delete your cluster, it's going to be cleaned up for you. So that's one way of using KubeRay to manage your simulators without really being Ray code or without having any Ray code in those simulators. So what we've done there is we've taken KubeRay territory. It was limited to the Ray cluster and your application code. And now we extended it to include the simulator pod. So that's one alternative way of thinking about KubeRay. It doesn't have to be limited to your code that you write with Ray. So let's go into the first demo. The first demo, we're going to create a Kube cluster using, we're going to create a Ray cluster using KubeRay. It's going to have mixed worker nodes, some Ray nodes, some simulator nodes, and then we're going to do some cleanup. Okay? So just to explain, okay, now I can see it. That's fine. I'm going to stand here. So to explain the setup here, here we're watching for pods that are related to Ray cluster. Here we can just watch for array clusters, and in here we're going to run some script. That's my demo. Does it say demo 1 here? Yeah. 2. You're gonna see it's gonna have a lot of text there, so yeah, it's not gonna have a lot. Okay, demo 1. So first thing we're gonna do is we're doing a kubectl apply for a certain YAML file, which includes a heterogeneous array cluster that has both simulators and workers. And here you can see that we have now a cluster of 3 pods. One is the array head, one is the worker, and the other one is the simulator group. And next, what we're going to do is just to look into some code that we're going to run inside one of those pods. It's a very simple code. It just says, print all the available nodes you have in the cluster. And that's it. There's nothing too complicated. This example is available on KubeRay GitHub repos. It's a sample example. Not the cluster manifest, but the code here. So let's go ahead and describe what that pod looks like, the one that's at the bottom here that has the simulator in it. And I'm mainly grabbing for the image there. And what I wanted to show is that image has nothing to do with array. In fact, for those familiar with Kubernetes, that's the pause container. That's just an image that has that does really nothing. It just sleeps forever. And now if we go ahead and execute that machine learning app that we just showed, it's going to check within the cluster nodes. And here you can see that it only showed us 2 nodes. I'm going to click here and go to another window that you cannot see. And that's the array dashboard. And in this array dashboard, if I go to the cluster, oops, that's a different one. I'm going to close this one. Well, it's just mainly to show that the array dashboard is showing that we have only 1 worker node. We don't have multiple of those. OK, I'm going to go back to my demo here. I'm just going to do some cleanup. So what we showed in this demo is that you can have an array cluster. And in that array cluster, you can have a mixed worker nodes. Some of them are simulators. Some of them are not. Some of them are array nodes that are array workers there. Now, moving on to the next use case, we're going to use array as a building block of a bigger solution. So instead of having array as a one-stop solution, we're going to assume we have a use case where we need more than just one engine, more than just array. And this is the case of data processing. So imagine now we have a bunch of data that we want to use it for reinforcement learning. Typically, in such environment, we call it offline RL. And the data that would be useful for the agent there would have to be formatted in a certain format. So you'd have state, action, reward, and next state. And sometimes you can add terminal flag there, or whether this is a terminal state or not. But it's expecting a certain format. What I'm trying to say here is that you're expected to process that data in a certain way before using it. And one way of doing that is you could take raw data, use some data processing framework like Spark or Flink or Splunk. And once the data is ready for training, then you can feed it to array and just use it for your reinforcement learning or machine learning for that matter. Now, the point here is that this data might not be training ready. And you might be using a different data analysis framework or engine to prep that data. That's not array, for example. And the question is, how should you be processing that data, and how can you be deploying those data analysis framework? So one example we're going to show today is using Spark. So assume you have Spark. You have a Spark application or a Spark cluster. So on Kubernetes, the Spark operator uses the terminology Spark application. For KubeRay, we use Ray cluster. But assume you have now a Spark cluster where you're going to load the data, transform the data, then save it, then pass it around to another cluster that you're going to create, which is the Ray cluster, use the data, train the model, and then save the model. So if we take that view and we flatten it out, you might be using, on top of Kubernetes, some orchestration, like Tecton for a pipeline or your own orchestrator. And then you could be spinning a Spark, using the Spark operator, you could be spinning a Spark cluster, process the data, and then save it. And then after that, you use KubeRay to spin up a Ray cluster, and then process the data there. And that would bring us to demo number 2. We're going to create a Spark cluster using a Spark operator, which is available open source as an open source project. And then after that, we're going to move into a Ray cluster. OK? So the first thing we're doing is showing some of the Spark code we're going to be running. It's simple code. All it does is does pi calculation, and it's going to be using 2 executors. So what you're about to see on the top left-hand side here is that you're going to have a Spark driver and then 2 executors that are running once we create that cluster. So now we're going to use kubectl apply for that cluster definition. Now you can see that the driver is running. What's going to happen is that the Spark operator is going to spin up 2 executors, exec1, exec2. And then I'm watching here at the bottom just to make sure that I only spin up the Ray cluster once the job is completed. So the first driver there is going to go from running to completed at some point. And then it's going to clean up on its own the executors. And then I'm going to create after that the Ray cluster. OK, now you can see that Spark has finished calculating pi. One thing to note here is that the result for pi calculation, 3.14, ending with 104, I think. Yeah, it's not that accurate, but it does the job. So now we're going to create a Ray cluster. Ray cluster has a simple application, just like the previous one, except here it's also printing that value that we're passing for it by mounting it into that Ray cluster. And now kubectl execute this Python code. And it's similar to the previous one, except here you're going to see some information about that pi that was read. And it should show the same result that was shown before, which is the one ending with 104 over there. And if we click on OK. So this is the job. You can see if I click on it, it just ran right now. And if I look at my Ray cluster, it's just a simple cluster with one worker and 1 head node. And that's all what's going on there. I'm going to close this window. And that would conclude demo number 2, which is using both Spark and Ray, both in Kubernetes, both managed by Kubernetes operators. And by the way, those are real clusters. The one that you see spinning and coming up in 10 seconds, 10, 15 seconds, those are fully fledged clusters. Like, you can use them for any of your applications. There's no shortcuts there. So let's clean up. Clear. OK, so for the final part, which I think it's the most fun, it's developing applications on top of KubeRay. So if we now take the developer corner and not just the data scientist corner or machine learning expert corner, as a developer, if you're tasked to develop a service, let's say you are tasked to develop a machine learning as a service portal, allowing practitioners to use your portal to train their model, and you want to be creating all those jobs or clusters in the background, you don't want to expose them to any of that. Now, you would want an SDK. You would definitely be asking for such an SDK that allows you to spin up clusters, interact with KubeRay, and then complete the job without you as a developer having to interact with Kubernetes and the infrastructure, and definitely without your users and the users of your portal having to do that. So this is where we introduced the KubeRay Python SDK. It's just a library that you can use with KubeRay. It's intended for managing Ray clusters, and it uses KubeRay under the hood. So basically, it's producing the YAML manifests that are consumed by KubeRay. It abstracts that from you. So you, as a user, you wouldn't be needing to work with Kubernetes as long as that application that you develop is deployed. Then you just interact with the application through whichever web interface you want to interact with. You don't need to deal with the infrastructure. It does CRUD operation, create, read, update, delete. And it's easily can be embedded into your own application. And when I say it can be embedded into your own application, imagine you're writing a Python application that's doing some machine learning. You can use this library. Your Python application is now running inside a cluster, array cluster. You can use this library to spin up more workers, to update those workers, to replicate or duplicate those workers, and so on. So as a flow, it would be like the Python SDK is going to act on a KubeRay. KubeRay is going to act on creating Ray clusters. Your code is going to be hosted on Ray clusters. And finally, your code is going to be using Ray code within those Ray clusters. I want to talk a little bit about that Python SDK and the hierarchy we use there. So we're using the director design pattern there. So the director is just a class that allows you the highest level of abstraction. So this is all the code you need, for example, to create a cluster. This code is a bit prescriptive because you can see here that it's saying build small cluster. But that means that you don't have a lot of configurability there. You're just going to ask it to build a small cluster. It supports 4 types: basic, small, medium, and large. Large has 5 workers, medium 3 workers, small 1 worker, basic only a head node. And that's it. And then after you create the cluster definition, you just create it, and you're going to have a cluster up and running. Now, the builder is another class that gives you more control. So instead of the director, where you're asking for a cluster with a t-shirt size, with a builder, now you can pass in more parameters. And here, for example, we're passing for the head node. The CPU limit is 3. For the worker groups, we're specifying the number of replicas. And there's a whole lot more attributes than this, that I'm showing here. Most of them have default values. The ones you choose are the ones you override those default values. And finally, in the lowest level, you would have the row API. And within that row API, you define your cluster definition whichever way you want. It gives you like the most flexibility. Anything you can do with a YAML file, you can do with the row API. And then it can create your cluster for you. Now, for those who are familiar with implementing the director pattern and using factories, you would know that the director under the hood uses the builder under the hood uses the row API. They're just different level of abstractions of how you would be interacting with the KubeRay cluster. Now, what we added on top of that is just some utility libraries. I mentioned a few functions of them earlier, like changing the number of replicas in a given worker group. You can update the worker group memory, CPU, GPU, et cetera. You can duplicate a worker group, give it now a different name, and now you'd have 2 different worker groups that are mainly identical except for the naming. And then you can delete a worker group once you're done. So for example, if you're using the same array cluster for serving once you're done with training, then you can delete the worker group that did the training and just keep the worker group that's going to do the serving. So from a high-level perspective for the demo, we're going to show the users. I'm not going to show the web server today. The web server was developed within a hackathon that we did. A group of contributors contributed to this demo. And from the web server, we go to the Python backend. The Python backend is simply just a Flask web server. It exposes some APIs. Under the hood, it uses the Python SDK I mentioned, talks to Kubernetes, invokes KubeRay, creates your cluster application. Some of those applications are using Azure Blob Storage to download files and to train based on those files. So let's go into this demo where we're going to submit a machine learning job request, show the Python job handler reacting to that request, and then clean up after. By the way, this demo requires internet connection because we're going to Azure Blob Storage. And I found that the conference connection is a bit finicky, so I was seeing some issues with that. OK, so what we're doing here is just a curl API. It's a post API. And that API, what we're saying is we want to create action equal create. The cluster name is demo. The namespace is default. And the size is small. That's all what we included in this API there. So once we invoke this API, we already have the Python application running in the background. And you can see it created for us a cluster just based on an API call that has nothing to do with Kubernetes. And you might be thinking this might be complicated code, but the entire Python backend is less than 300-400 lines of code that can manage your clusters. It exposes an API for create clusters, delete clusters, get a single cluster, list clusters, and execute commands within a cluster. So now I'm going to use the get command. It's going to show me all the information related to that cluster. It's not going to look that clean, but it's whatever Kubernetes is giving back information about this particular cluster. And then I have some machine learning application that's running inside this, that's going to run. I haven't executed. I haven't invoked it yet. But what it does is just it does some training. It's using the XGBoost library. And then it's loading a file from Azure. You can see here we're using the AZ scheme. This is being downloaded from Azure. And then after that, the part that we haven't shown before is this one here, which is the array serve. So up to this point, you were doing the training. And then after that, in this part here, this is all it takes for you to do serving on the model that you train. And you can see we're exposing an API / breast cancer / inference. And this is the one we're going to try to hit with our API after to see if that model is serving properly or not. So I'm going to hit execute. This is now going to run this code. First, downloading the training data set. And then it's going to take a few seconds. Yeah, I'm going to try that again. Same thing, we're going to post. It already exists. Then we're going to do the get. It's the same thing. Then now we're going to try to execute. Let's see if this time the internet works. OK. So let's see. So what we have here, we have the cluster now is first serving inference after it finished the training. And we're going to issue just some curl commands to see if that inference is going to serve our request or not. So I'm just basically passing to it some numerical values, and it's going to reply whether this is a positive or a negative cancer diagnosis. Nothing special there. The inference itself, I just clicked enter a couple of seconds ago. And here you can see the cancer prediction is false. And it doesn't take much. It takes less. You can see here it's written somewhere how many milliseconds it takes. So it takes in the order of milliseconds. It says here 11 milliseconds to process that request. But let me try it one more time. We're doing another inference, again, based on the same model. And finally, let's try to see the cluster itself. I'm going to click on this link. Going to find my, okay, I have to go this way. So these are the jobs that I ran before. There's one that's running, still running. This just ran right now. But if I click on serve, now you can see that I am using Ray serve on this endpoint that I just defined. And then if I click on my cluster, this is the cluster that we have running that's called demo cluster. And all of that was created using the curl API, which is just a RESTful API that was exposed by a Python application. So what we've just shown in this demo that you can really just use the Python SDK to develop a job handler. The job handler can create Ray clusters for you on demand, execute workloads on those Ray clusters, and you don't have to worry about any of that. And the same API allows you to create, update, read, and delete those clusters. So let me summarize. In summary, we just shown today 3 different shades of using KubeRay. We used KubeRay as one-stop solution. It had the simulators, your machine learning code, all running in the same environment. We showed a different use case where we had Ray as a building block in a bigger solution. We had we had Spark cluster doing data processing, and then after the Spark cluster completed for processing, it was removed, and then the Ray cluster took its place and started doing the machine learning there. And finally, we developed a job handler based on a Python SDK that we define that comes with KubeRay. So final thoughts, as a user of KubeRay, you typically have lots of tools in your hand. You have KubeRay, you have Ray with serve and so on. You have the client libraries. So what you do there is really up to you and how you come up with different ways of using KubeRay. And don't think of a Ray cluster just as a pet. I mean, you can treat them as cattle. You can, in this demo alone, we created and removed 3 or 4 Ray clusters. It takes just 10, 15 seconds once the image is already on the Kubernetes cluster, and that's it. I think I ran over my time. I just want to give acknowledgments to the KubeRay community, Anyscale team, especially the maintainers of KubeRay, and Microsoft Bonsai team and data analytics team.